So, back to mechanics, obviously. Now, what you've done in mechanics in the past has all been kind of in just straight lines, yeah? So you've looked at forces going horizontally, you've looked at forces going vertically, right? You've looked at accelerations, all that kind of stuff. What moments are a force that creates a turning action. All right. So, for instance, if I have this rod, right, so it's a rod like this. If I fix it at one point, okay, and I apply a force, right, up, what's actually going to happen is we're going to get, well, from your perspective, it will be a clockwise direction. So it's not going to go up like you've had before. It's not going to go sideways. It's going to have a rotation like this, okay? And that's what moments are all about, right? Even if there's no actual rotation happening, right? When you're taking moments about a point, you're looking at any sort of potential clockwise or anti-clockwise turning moment that's happening, right? So I'm sure you appreciate that when you have a door, all right, when you open the door, why is the handle at this end, this side? Why don't I have a knob in the middle or at this side of the door?
Large movement.
Okay.
More distance from it.
More distance from your foot, right? So if I try to hold the handle there and pull, what's going to happen?
Going like much farther.
Okay. Right, so I need more force to get it. And that's the fundamental thing here. So this is what, so your moment, okay, about a point is the force that's being applied times the distance which away from the point at which you're applying. Okay? So obviously if I try and turn this ruler like here, I'm having to push quite a lot because the force to get it to move, the distance is smaller, so I have to apply more force to lift this ruler. If I do it at this end, it's really easy. All right. So I need to get the same moment. I need less force because the distance away from the pivot point is further. Okay. So that's basically what we're doing now. Just to kind of introduce you to situations that we might be in. So, for instance, if I were to rest this like this, right, and just hold it, imagine my finger is just a pin, right? Do I have any moments at the moment? Do I have any rotational forces happening?
No.
Okay? What? You say no, no.
I would say you prefer slow. So it's an object at rest stays at rest when slow force is active.
Okay, but there are forces acting on this. Exactly. Gravity is applied, right? So, what forces are being applied? Well, gravity is being applied. So that is gravity, right? The weight is gravity acting. What other force is being applied?
Force of your finger on.
Force of my finger. Okay. Now this is fixed at the bottom here. Imagine that's a pivot, right? What direction of what direction is the weight causing the ruler to move it?
Anti-clock.
So from you, it would be the weight is applied from the center of mass, which in a uniform, we call this a uniform rod because ignore the handle, it's the same all the way. So the center of mass is here. So this mass is pulling down. Okay. Now, this is, if I look at this pivot point here, which direction is this weight pulling going? Is it going this way or is it going that way? Is it going that way? So is that a clockwise or an anti-clockwise?
Anti-clockwise.
Anti-clockwise. Okay. But if I consider this pivot point up here, which way is the weight going now compared about this point? Clockwise, it's going this way, right? And that's the fundamental thing with moments. It's being able to identify which point at which you're taking moments, which direction those moments are going in. Are they going clockwise or anti-clockwise? So we've got the weight here, okay? If I take this as my pivot point, right, I've got the weight. What about this over here?
Anti-clockwise.
Well, this isn't actually doing anything because the centre of mass is here. Now, if I did apply a weight, if I hung a weight on there, it would be trying to pull it that way out, right? So that would give me that direction of rotation. Now, again, if we go back to this point though, this mass here is going that way. What about here if I added a mass, what direction? Still the same direction, yeah? So you notice if I do it about this point, everything is turning it in the same direction, regardless. But if I take a moment about this point, I've got different directions. Now you're right in saying when something is in equilibrium, what do we know about all those moments?
They're all equal.
They all balance each other out. So instead of vertical and horizontal forces cancelling each other out, we now have
Clockwise and
clockwise and anti-clockwise moments that will cancel each other out, or balance each other out. All right. As I was saying before to the people that have just arrived, the important thing about a moment, how do we work out a moment? Well, it's F times D, because if I go closer to the pivot, because the distance is shorter, I need to apply more force to get the same moment. If I go further away, it's a lot easier. Hence why a door handle is at the end of the door, not in the middle of the door. Right? So, I don't know whether you want to write any of this stuff down. Those of you that have just arrived, if you took the reset, I can show you a paper at the end of the lesson. I didn't mark it, Mr. Vaughan did, so I need to go through it myself, but can't keep it, but I'll let you have a look. All right, so moments is a turning force, but what we do is we calculate it as force times distance, and it is the perpendicular distance from which the force is applied. So you'll notice on this one, which way did I apply the force? I applied it up, straight up, okay? So the distance that I'm considering is perpendicular to that straight up, right? And that gives me my rotation, but my force is always pointing straight up. The units of moment, and this is important because I remember doing a question with my upper sixth, and we were struggling to figure out why we weren't getting the right answer. It was purely because it wasn't in meters. So the units, just like you've had some of those in your IGCSEs where, you know, they mix the meters and centimeters of a question. So the units of moments are Newton meters, right? So force is obviously always in newtons. The distance is always in meters. So you always have to convert that otherwise, all right? So this, by the way, is where it starts. This is fundamental. This is perpendicular distance from the direction of the force, because it starts very nice and easy where the forces just apply vertically or horizontally, but when the questions get harder, they change the angles at which the forces are applied. So we have to resolve forces and things and then do, which is why I say it can get quite difficult. So we've already discussed here, look, the moment will either cause a clockwise or an anti-clockwise rotation. Right there, Jake, do you need me to put it back or?
Yeah. Yep.
All right, so clockwise or anti-clockwise movements. You write this down, Ethan?
I haven't finished it.
Oh, you've already done it. Okay. You can lead on this then. This will be good.
maybe the more complex part out.
We won't get to any complex ones today. I've got a few easy examples. You can lead us through them. That'd be awesome. All right. You ready, Jacob? Yeah. Done what you need? I am recording. I forgot. Okay. Now, we have two. To start with, we have two types of thing that we're going to do with it. So we have a uniform rod. That's what I was talking about. Right? Imagine my ruler is a uniform rod, but equally, you can imagine forget it's three-dimensional, imagine it's two-dimensional. A shape such as this is a lamina. So basically a two-dimensional plane. Right? And the same thing can happen with a lamina, which is I can hold it, I can fix it about one particular point, and then where's the center of mass of this book? Center of the book. Okay, so that point there that it shows, so mg, you're where the mass times gravity. But I can sort of rotate it about other points. So if I hold it there, well, you must have done this in the past, the weight makes it turn, right? If I hold it there, the weight makes it turn, right? How do you think I calculate the moment, the turning moment, using the weight on a lamina?
It's force.
Yeah, so that's the force. So I'm just going to do force times distance. All right, so the force is acting down. And what we're interested in is the what distance, because I said this was super important. That,
Distance from pivot.
yeah, but I said something else that was very important. I said the perpendicular distance to the line acting on the force. Okay. All right. So in basic, that's what we're looking at. We've got either uniform rods. They can be sort of held at particular points. I showed you my finger was either a part way along or just at the end or wherever the pivot point is about which we might take the moment. We can take it about different points. So I said on the lamina, we can, for instance, you'll see, what if I were to hold my lamina like a flag or a sign? I've got 2 points here that I'm holding it. It's not rotating at all, but are there any moments happening? Yeah? Where?
Like a flag, so it can like go to the sides.
Well, both points, yeah? So I've got moments about that, so it is trying. And I've got moments about that one, so it's trying to rotate, but they're stopping each other. All right? Now, sometimes there might be other things holding it as well, depending whether it's a sign that's been held. But even if it's not moving, all right, we do have moments. So, for instance, if I hold it at this point up at the top corner, which directions have I got moments happening?
Down, clockwise.
Right, so it's going, is that clockwise? Yeah, clockwise. But if I've got this one, clockwise, yeah. All right, so if I take moments about this point though, right, I have got the weight pulling it that way, but what's this one doing?
Putting it up.
Pulling it this way, yeah? Hence, if I take moments about the bottom point, this point becomes a force that's applying a moment in the opposite direction. Right? So it's about really considering which directions we're going. So let's have a look at just a couple of basic questions then. Over to you, Ethan.
So,
You want to write this down, guys, so you've got examples in your. So we've got a uniform rod. What does uniform mean again? Mass is equal all the way through. All right. So where's the center of mass?
midpoint.
In the midpoint of the rod. Okay. If it was a non-uniform rod, you've taken further maths, that would change that. So we've got a uniform rod, has a weight of 5 newtons. Point P is at one end of the rod and point Q is 5 meters from P. Find the moment of its weight about the point. So, always with the diagrams then. Always with the diagrams. What's the diagram going to look like? Well, obviously we've got our rod, point P here, point Q here. What's this distance? This is, it says, 5 meters. What's this distance? 1 meter. Okay. So what are the forces being applied and where? There is only one sort of force that we're looking at, which is the weight. So where shall I draw that? The middle. Okay. The middle of P and Q.
In the middle of the time rod.
Okay. So I'm going to put it here. Right. Right. It says uniform rod 5 newtons. So that makes this a 5 Newton force. Okay. So what are the moments? What are the moments about point P? So we're basically asking what effect, what turning effect is being applied around point P by the weight?
2.5 times.
Careful.
0.
So the moment is equal to force times distance. We said that. So I'm after moment. So what's the force? 5. The distance is 3. Why 3 and not 2.5?
It's the whole rod.
The whole rod. Yeah. It's not the difference between these 2 points. This mass is acting from the center of the rod. The turning effect is in which direction? That direction it's going to go in. So it's going to go clockwise. Right. So it's the force 5 acting at a distance of 3 meters. Okay, that's the confusing bit. So 5 meters or whatever. But so we have 15 Newton meters clockwise. Okay. What about the moments about point Q then?
Distances. Wait, where do we start from there?
Q. So if I'm taking moments about point Q, I'm now looking, it's the same.
But it's just 2.5 meters now.
Okay, so I've still got 5, but this time it is, yeah, that distance, isn't it? So the distance this time is
2.5.
no
2.
2. Why is it 2? Because that whole distance is 3. We know that's 1, so it must be 2. So it's 2. So we've got 10 Newton meters. Which direction? Anti-clockwise. So it's going to go that way. Okay. Does it sound right so far? I mean, this is pretty basic stuff, but this is kind of only the introduction to moments. So it's good. We really do need to understand this kind of concept of anti-clockwise, perpendicular distance, all that kind of stuff. All right. All good. So let's have a look then at the next question. So uniform rectangular lamina measuring 0.4 meters by 0.6 meters has center C. So you put in a center C and a weight of 8 newtons. So where does that get marked on our diagram? From the center. So that's down. So that's your 8 newtons. Okay. Center of mass of the lamina, assuming it's a, well, not assuming, we're told it's a uniform lamina. Okay. So find the moment about P. Well, we've got two moments happening, the weight and a 12 Newton force. Why? We only had one moment about each point here. We just had the moment about P is just one of them, and then about Q is the other one. Why do we have two moments about point P? What are they?
Angular lamina.
Why two? We could just have one still. Are you sure it's anti-clockwise and clockwise? So just P, yeah, we've got point P. That's all we're worried about. It's not. There's no point Q. So C here, this weight that acts from point C, which direction is it going? So around point P, it's going to create a clockwise moment. Okay. Now it says the lamina is free to rotate in a vertical arc, but we've got this other force being applied. So that's like me holding the book and applying a force this way, but I'm not pulling it along like that, like a truck being pulled by a thing. I'm pulling it and it's going to make it go down, right? So actually, this 12 Newton force, what direction are we going to be creating?
Right.
It's actually another clockwise moment about point P. Yeah. How could I get an anti-clockwise moment?
Up.
Moment on the top one.
Or top.
Yeah, so if I went this direction, okay, it would create. Or yeah, you're right, if I went from that and pulled up, I would also create.
Then you could do it at any point.
Yeah, if I pulled this point, pulled up, I would get one in the opposite direction as well.
You should do P as well.
Well, it's all, well, no, I can't. Why will there never be any moment about P by putting a force through point P? Good, that's the answer. There's no distance. Distance is a thing, yeah? So if you have no distance about your pivot point, there is no moment there, yeah? You can't, I can't take this rod here. If I hold it at that point, how can I apply a force that turns it at that point? I can't, right? Same thing. It's like, imagine trying to open the door by pulling on the hinge. Right, I can't, even if there was a handle there, I can't do anything, can I? Never going to be able to open this door by holding the hinge and pulling. There has to be some distance away from the pivot point. All right? So, we have in this question, we have absolutely no anti-clockwise. All right, so let's find the moment of about P of the weight. What is that moment? So again, a moment is force times distance. So the force is 8 newtons. What's the distance?
Pythagoras.
Well, I've got 0.2, 0.3, and Pythagoras. Which one?
Surely you'd be diagonal. You'd have to calculate it.
You've missed the point that I talked about.
It's still the same
Perpendicular.
as. It's still.
So what did I say? It was fundamental to this. When it gets harder, you have to remember, and it is tricky, I'd say, but so we have to really ingrain this now. What we do is we look at the action of the force. The line of action of the force is vertically. So then we go from that action and we go perpendicular to the point, and that's the distance. So what is that distance? So that distance is 0.3. So we're going to go 8 newtons times 0.3 meters, and we get the answer 2.4 Newton meters. Okay? So that's the fundamental, guys. Absolutely fundamental is look at the direction of the force that's acting, and you have to find the perpendicular distance. So let's look at the 12 Newton force. So the line of action of the force is up here. Okay, so we need perpendicular is 0.4. Okay, so the moment of the 12 is 12 times 0.4, which is 4.8 Newton meters.
So you can extend the moment or the force
Well,
No, you do it from.
because that force was shown at the corner.
okay, so yeah, that's worth talking about. This arrow, there is no force along the magical arrow, is there? We're just saying that's the line of action of the force. So you're extending that line just because that force is being applied in that direction, right? I guess if you were drawing vector arrows and things, the length of the vector would signify the magnitude of the force, but we're not really looking at that. We're just looking at the direction of the line, and then we go perpendicular. Now you could, if you like, just go, well, I could take this from this point and go to there is 0.4. It's perpendicular. It reaches, but it's easier. Like people say, it's easier to extend that line until you can go perpendicular to your pivot point. Yes.
So what's A? Is A 4.8 plus 2.4?
No, they're separate.
So
The moment of P that the weight is
so that's
causing
the 8 Newton.
is 2.4 Newton meters.
Okay.
B is 4.8.
Okay.
Now, what is the total moment applied around point P? That would be 7.2.
7.2.
Yeah, so the total clockwise would be 7.2 Newton meters. So what would that lamina be doing? Turning, yeah? There's nothing holding it the other way, so it would be turning. All right, okay. Over to you. What does resultant moment mean? Yeah, so you're going to have to considering all the clockwise and all the anti-clockwise. They will cancel each other out, and you'll be left with a force going in one of the two directions, or they'll cancel each other out completely and it won't be rotating. So you've got a rod, you've got point P, you've got distances, you've got your weight, you've also got two forces being applied at either end. Okay, so we have to, I'll do this bit with you, but you can do the rest. So what's this? Point P, which direction is this 10 newtons going to be going? So that's going to be a clockwise one. This 7 Newton one is going to be a, nope,
Oh, no,
also clockwise about this point. But this one, 3 newtons is going to be a anti-clockwise moment. Okay? So find the resultant moment. So basically, find the resultant moment means which direction is it turning and with what force. I'll leave you to work it out. And so I think you've got it. If we do, I'm going to do all the clockwise ones first. So that is
2 times 10.
7 times
2.
2 plus
2 times
10 times 2, just to keep it consistent. 14 and 20 is 34. So my clockwise moments are 34. My anti-clockwise is just
6 times 3.
3 times 2. Obviously, that whole thing, that's the middle, so that's going to be 4 as well. So 3 times 6, which is 18. Right. So
34 minus
Like-
18.
34 minus your 18 is 16 Newton meters, and it's going to
You
be
got it wrong.
clockwise.
No.
Okay, easy enough.
Yeah.
They do
Yeah.
start quite easy. Over to you then for a bit of practice. Exercise 2A, page 507 is the start of it. Okay. Exercise 2A, page 507. And while you're starting with that, I can show those that have got there.